Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. For part number 5, we will discuss about air conditioning processes. The purpose of the air conditioning processes is maintaining a living space at the desired temperature and also humidity. As I mentioned before, the human comfort depends on the few factors such as the temperature, humidity, and also the airflow. So we will use the air conditioning process in order to maintain the temperature, the humidity, and also the airflow of the air in order to maintain at specific value to confirm the human comfort. So there are a few processes involved in the air conditioning process to make sure the human comfort. So the figure shows the simplified psychrometric chart, and the arrow shows the processes that involve in air conditioning process. There are a few processes involved. First, we have heating process, cooling process, humidifying process, dehumidifying process, the combination of heating and also humidifying, and the last one, cooling and also dehumidifying process. So basically, we will have 4 basic process involved in air conditioning system. First, we have simple heating. The second one, we have simple cooling. So the schematic diagram shows the the system for heating and also cooling, where we can see that the system will have a coil that represent heating coil and also the cooling coil. Okay, so the air will enter the air ventilation, and for the heating process, the working fluid in the coil will be the hot medium, such as steam, hot gas, and so on. So this heating coil will release heat to the air, and the temperature of the air will increase for heating process. Okay, so at the inlet we will have the condition in terms of temperature, specific humidity, and also relative humidity. So for heating process, the temperature of T2 will increase, and normally the value of specific humidity will be constant. The change of relative humidity depend on the process, whether the process is heating or cooling process. For simple cooling process, so we will have, instead of we have heating coil, for simple cooling we will have cooling coil. So inside the cooling coil we will have working fluid such as the refrigerant or cold water, and this refrigerant or cold water will absorb heat from the air, so that the temperature of the air at the outlet of the air ventilation will decrease. Similarly, to the cooling process, the specific humidity also constant. However, the relative humidity will change. The third process we call humidifying, where this process is to increase the moisture content in the air. And the last one, we have the process that we call dehumidifying process, where the purpose of this process, we want to reduce the amount of moisture or water vapor inside the air. Okay, so this is the schematic diagram for the dehumidifying process. So for dehumidifying process, we need to use a humidifier. So normally this humidifier is referred to the spray system, where in the system the hot water or cold water will spray into the air. Okay, so by spray the water, the moisture content or water vapor inside the air will increase. Okay, so normally the process will combine 2 different processes, such as heating process plus humidifying, or cooling process plus dehumidifying. Okay, the last process is the dehumidifying process, where we will reduce the amount of water vapor inside the air. So normally we will use the cooling process, so that the water vapor inside the air will condense and remove from the air. Okay, so these are 4 basic processes in air conditioning system. And in terms of analysis, in terms of equation that can be used in these air conditioning processes, we will use the steady flow process, and we can implement the mass balance equation. So we have two types of mass balance equation. First, we have mass balance equation for the dry air, where MA in dot mass flow rate in for dry air equal to mass flow rate out for the dry air. The second equation is for mass balance equation for the water vapor, where the total mass flow rate for the water vapor in will be equal to total mass flow rate for water vapor out. Okay, or we can we can change the equation based on the specific humidity equation. So the total MA dot multiplied by omega in equal to the total MA dot multiplied by omega out. And then also we can apply the energy balance equation. So because the process is steady flow process, the rate of energy change of the system will be 0. So we will get this equation in terms of energy balance equation, where Q in dot plus W in dot plus total E mass in equal to Q out dot plus W out dot plus total E mass out. So these are the equations that can be used to analyze the air conditioning process. Okay, for air conditioning process, first we look at the simple heating and also simple cooling. So the main criteria for simple heating and also simple cooling is the value of omega at the inlet and also at the outlet of the process is constant. And in terms of relative humidity, for simple heating, the value of relative humidity will reduce at the outlet of the process. So this is the schematic diagram for the heating process, simple heating process, where we have the air ducting system. So we have air ducting system inlet, referred to state number 1, and also air ducting system outlet, that's referred to state number 2. So at the inlet we have the parameters such as temperature, dry bulb temperature T1, specific humidity omega 1, and also relative humidity psi 1. So at the outlet we have the temperature, dry bulb temperature T2, specific humidity omega 2, and also relative humidity psi 2. So for this process, the value of omega, specific humidity, will be constant during simple heating process. So omega 2 equal to omega 1. However, the value of relative humidity at the outlet will be less than relative humidity at the inlet of the ducting system, air ducting system. Okay, which means the value of specific humidity constant during the simple heating process, and the relative relative humidity will reduce for the simple heating process. So in the air ducting system, so we will have heating coil, while inside the heating coil we will have hot medium such as steam, hot water, and so on. So this heating coil will release heat to the air so that the temperature of the air will increase. Okay, so in terms of mass balance equation for the dry air, MA dot 1 at the inlet will be equal to MA dot 2 at the outlet, equal to MA dot. So mass flow rate for the dry air will be constant, and the value of specific humidity for the process is constant, where omega 1 will be equal to omega 2. So if you want to determine the amount of heat released by the heating coil, so we need to implement the energy balance equation. So for the heating process, we will not have any any work in or work out. So for this case, we will have heat release to the air. So at the end, we will get the value of Q, heat transfer to the air. Q dot will be equal to MA dot multiplied by H2 minus H1, the enthalpy difference between the enthalpy at the outlet and also the enthalpy at the inlet of the air ducting system. Okay, or we can write in kilojoule per kg unit. Small letter q equal to H2 minus H1. So if we want to draw the process by using the psychrometric chart, so we can draw the simplified psychrometric chart as shown in the slide. We just draw the frame of the psychrometric chart, and then we draw the line, the important line that involved the process, where we have constant line for the specific humidity for omega 1 equal to omega 2. So we just draw the horizontal line, and then we draw the what I call the vertical line for the dry bulk temperature at state number 1, T1. So we have state number 1. For state number 2, we know that what we call the temperature will be increased due to the heating process. So the location of T2 must be greater than the temperature of T1. But still, the point of intersection the point of intersection must be on the same constant specific humidity line. Okay, so we have state number 2, and we have, let's say, the value of psi 1 equal to 80% due to the heating process. So we will get the value of psi 2 less than psi 1. So in this what I call process, we just write down the value of psi 2 equal to 30%. Just an example in order to show that the value of relative humidity reduced during the heating process. Okay, so this is how we want to show the process on the simplified psychrometric chart for the simple heating process. Okay, the second one is the simple cooling process, where for the simple cooling process, the value of relative humidity will increase at the outlet of the process. So the in terms of schematic diagram, the schematic diagram is similar with the heating process, but now instead of we use heating coil, so now we use cooling coil. So inside the cooling coil, we will have a refrigerant or cold water in order to absorb heat from the air. Okay, so we have state number 1, inlet condition, where we have T1, omega 1 and also psi 1. State number 2, the outlet condition for the air ducting system, where we have T2, omega 2 and also psi 2. Okay, so for the simple cooling process also, the value of specific humidity will be constant, where omega 2 equal to omega 1. However, the value of psi 2, relative humidity at the outlet, will be greater than relative humidity at the inlet of the air ducting system. Okay, so if you want to describe the process by using the simplified psychrometric chart, so we just draw the the basic frame of the psychrometric chart, and because the process involves with constant specific humidity, we just draw the horizontal line for the specific humidity to represent the value of omega 1 and also omega 2, and we plot the intersection point for temperature number 1, T1, the temperature at the inlet, and we have state number 1, and due to the cooling process, the temperature of T2 must be lower than the temperature of T1. So we get the second intersection point between omega 2 and also T2. Okay, so if we draw I call the curve for relative humidity, so let's say psi 1 equal to 30%. Due to the cooling process, the value of psi 2 will increase, let's say become 80%, and the process for the simple cooling will start from state number 1 to state number 2. So this is the how to describe the process for the simple cooling by using the what I call the simplified psychrometric chart. So these are the main criteria for the simple heating and also simple cooling. Okay, so if we compare with the heating process, for simple cooling process, in terms of Q, we will have Q that absorbed by the cooling medium. Okay, but in terms of equation, we will use the same equation where we have we have Q dot equal to MA dot multiplied by enthalpy difference. Okay, multiplied by enthalpy difference. So we need to use the energy balance equation in order to get the equation for Q dot or heat transfer during the cooling process. Okay, the next process, or the third and also the fourth process for the air conditioning system, involves with humidifying process, where we want to increase the amount of water vapor or moisture in the air, and also the process that we call dehumidifying process, where we want to remove the amount of moisture and also water vapor inside the air. But normally these processes in terms of humidification and also dehumidification normally combine with heating and also combine with cooling process. Okay, so for humidification, normally this process will combine with the heating process. So now we have heating plus humidification process. So this is the schematic diagram. So we have air ducting system where the system consists of two sections, heating section and also humidifying section. So in the heating section, so we will have heating coil, and for the humidifying section we will have the humidifier, or we call the water spray. So in this schematic diagram we have three states involved. State number 1 is the inlet of the heating section. State number 2, the outlet of the heating section, also equal to the inlet of the humidifying section. And the last one we have state number 3, we call the outlet of the humidifying section. Okay, so the air will enter, start from state number 1 until state number 3. So for heating, the main criteria will be omega 2 equal to omega 1. And for humidifying section, because during the humidifying process we spray what we call water, amount of water. So the amount of water vapor or moisture content inside the air at the outlet of the air ducting system will be increased. So that's why we have omega 3 will be greater than omega 2 during the humidifying process. Okay, so if you want to draw the process, so first we draw the process for the simple heating process. So we have constant specific humidity for state number 1 and also state number 2. So we just we draw the temperature T1 line to obtain the insertion point for state number 1, and then because the process involving heating, so the temperature increased to T2, so we have state number 2. Okay, and the value of relative humidity increase, the relative humidity during the heating section will decrease, let's say from psi 1 to psi 2. Okay, psi 1 equal to 30%, for example, and psi 2 equal to 10%. Okay, so for state number 3, due to the humidifying process where the moisture content increase, the value of omega 3 will increase compared to omega 2. Okay, so this is the process, what I call the process for heating, simple heating, start from state number 1 to state number 2. So for state number 3, because the process involved with humidifying process where we add more moisture content or water vapor inside the air, so the value of omega will increase. So we just draw the line for omega 3, where the line must be greater than the line for omega 1 and also omega 2, because the moisture content already increased at the outlet of the air ducting system. Okay, so we will have what I call different value of relative humidity. Okay, where the relative humidity during the process will increase. So we have the third point for the process that represent the state number 3. Okay, so we have these are the process involved for the heating plus humidification or humidifying process. Okay, so this how we can describe the process by using the simplified psychrometric diagram or chart. Okay, and then for dehumidification or dehumidifying process, normally we'll combine with cooling process, because in order to conduct the humidifying process, the process must involve with what I call the condensation process. So for the condensation process, the cooling process must be involved. Okay, so this is the schematic diagram for the cooling plus dehumidification process, where we have 3 states here: state number 1, state number 2, and so state number 3. And we will the process will involve cooling coil. Okay, so we have first we have cooling section, start from state number 1 to state number 2. So during the cooling process, the value of omega will be constant, where omega 1 equal to omega 2. And we have the second section is dehumidifying section, start from state number 2 to state number 3. So actually dehumidifying section actually also the cooling process, but the cooling process we must conduct the cooling process until the condensation will occur. Okay, so we need to reduce temperature until reach the dew point temperature of the water vapor inside the air. Okay, so when condensation process occur, so the water vapor inside the air will change into liquid and then will remove from the air. So now after the dehumidifying process, the amount of water vapor inside the air will be reduced. So at the outlet of this dehumidifying process, the value of omega will reduce or will be less compared to the value of omega 2. Okay, if you want to describe the process, so we can use the simplified psychrometric chart or diagram. First, we draw the constant specific humidity line for the cooling process. So plot the point for T1. Due to the cooling process, the temperature T2 will be reduced. Let's say state number 1 is at relative humidity of 30%. Okay, so now state number 2, in order to start the condensation process, state number 2 must be at least at saturation line. Okay, so this is the condition for state number 2, where state number 2 is at saturation line, where represent the saturated air condition. Okay, so we just draw the horizontal line intersect with saturation line, and then we need to reduce the temperature again until the condensation process will continue. Okay, so the arrow shows the cooling process, and then let's say until a certain condition where we have the amount of moisture content reduced, so that the value of omega 3 will reduce if compared to the value of omega 2. So omega 3 less than omega 2, we just draw the horizontal line for omega 3 intersect with saturation line, so we'll get the point for state number 3. Okay, and then we will have the point for state number 3. Okay, the point for temperature number 3, where temperature number 3 less than temperature number 2. So this is how we describe the cooling and also dehumidification process by using the simplified psychrometric chart. Okay, now we look at the equation that can be used for the analysis of the heating and also humidifying process. Okay, want to know the equation that can be used for heating with humidification process. So in the slide shows the schematic diagram for the heating plus humidifying process, and also the process, the process that shown in the psychrometric chart as we discussed before. So in terms of heating process from state number 1 to state number 2, in terms of dry, if you implement mass balance equation for dry air, so MA1 dot will be equal to MA2 dot will be equal to MA dot. So the value of mass flow rate for dry air will be constant in heating section, at the heating section. However, for water vapor mass balance, so during the heating section, no additional of water vapor or no removal of water vapor, so we will have constant, we will also have constant value of mass flow rate for water vapor, where MV1 dot equal to MV2 dot. Okay, so if we implement the specific humidity equation, so we'll get MA1 dot multiplied by omega 1 equal to MA2 dot multiplied by omega 2. So from this equation we can prove that the value of omega 1 equal to omega 2 during the heating section. Simple heating section. Okay, now if we implement energy balance equation, because during the heating process the hot water or hot medium inside the heating coil will release heat to the air. So we will get this equation where Q in dot, Q in means the heat that absorbed into the air. So we have Q in dot plus MA dot multiplied by H1 equal to MA dot multiplied by H2. Okay, rearrange the equation, so we'll get the equation for Q in dot for the heating process, the amount of heat released by the hot medium, or the amount of heat that received by the air. So we have Q in dot equal to MA dot multiplied by H2 minus H1. In the humidifying process from state number 2 to state number 3, if we implement the mass balance equation for dry air, so dry air still constant, where MA2 dot equal to MA3 dot equal to MA dot. However, for water vapor mass balance, this equation will be different if we compare with the heating process. So now we already add more moisture or water vapor inside the air due to the water spray during the humidifying process, where now we have MV2 dot, okay, at the inlet of the humidifying process section, plus the additional what called amount of water vapor or moisture, which is referred to MW dot, equal to the MV3 dot at the outlet of the process. So if we use the equation for specific humidity, so MA2 dot multiplied by omega 2 plus MW dot equal to MA3 dot multiplied by omega 3. So if you rearrange the equation, so we will get the formula for the mass flow rate for the water vapor or moisture content that add by the humidifier during the humidifying process, where MW dot equal to MA dot multiplied by omega 3 minus omega 2. Okay, so these are the equations that can be used during the analysis of heating with humidifying process or humidification process. Example 6.5. An air conditioning system is to take in outdoor air at 10 degrees Celsius and 30% relative humidity at a steady rate of 45 meter cubic per minute, and to condition it to 25 degrees Celsius and 60% relative humidity. The outdoor air is first heated to 22 degrees Celsius in the heating section and then humidified by the injection of hot steam in the humidifying section. Assuming the entire process take place at a pressure of 100 kPa, determine A, the rate of heat supply in the heating section, and B, the mass flow rate of the steam required in the humidifying section. Okay, the solution for example 6.5. First, we need to answer the question A, the rate of heat supply in the heating section, where we need to determine the value of Q in dot. Okay, first draw this schematic diagram and identify what I call the value or the data given in the question, and we can put the data given into on the schematic diagram. So in terms of data given, T1 equal to 10 degrees Celsius, which is equal to the dry bulb temperature at state number 1. Relative humidity Psi1 equal to 30%. Volume flow rate at the inlet V1 dot equal to 45 meter cubic per minute. The pressure of the air is 100 kPa. So if you look at the value of pressure, the pressure is 100 kPa. So we cannot use the psychrometric chart to determine the what I call the important parameter in this problem. So we need to use the specific equation. T3 already given, where T3 equal to 25 degrees Celsius, also equal to the dry bulb temperature at the state number 3. Relative humidity Psi3 at the outlet equal to 60%. And Cp normally given equal to 1.005 kJ per kg Kelvin for air. T2, the temperature after the heating process, also given, where T2 equal to 22 degrees Celsius, equal to the dry bulb temperature for state number 2. And the value of relative humidity at state number 2 is not given. The value of Ra, gas constant for the air, equal to 0.287 kilopascal meter cubic per kg Kelvin. So for heating process, we know that the water vapor content is constant, so that's why the important relationship that we know for the heating process will be omega 1 equal to omega 2. For the humidifying process, the water vapor increase, so omega 3 will be higher or will be greater than omega 2. In terms of equation, in heating section, in terms of mass balance equation, Ma1 dot for dry air equal to Ma2 dot equal to Ma1 dot. Okay, equal to Ma dot. So for water mass balance equation, in the heating section, so Ma1 dot multiplied by omega 1 equal to Ma2 dot multiplied by omega 2. So we will get omega 1 is equal to omega 2. So in terms of energy balance, so from this equation we can determine the equation for the rate of heat supply to the heating section, which is referred to the Q in dot. So Q in dot plus Ma dot multiplied by H1 equal to Ma dot multiplied by H2. So rearrange the equation, so we'll get the complete equation for Q in dot, where Q in dot equal to Ma dot multiplied by H2 minus H1. So in order to determine the rate of heat supply in the heating section, so we need to determine the value of Ma dot and also the enthalpy value for state number 1 and also state number 2. So the enthalpy value we can determine from this equation, where H1 equal to Cp T1 plus omega 1 multiplied by Hg1. Similarly to H2 equal to Cp T2 plus omega 2 multiplied by Hg2. So now we need to determine the value of H1 and also H2, where H1 we cannot get directly. First we need to determine the value of omega 1. So omega 1 we can determine by using the specific equation. Cp already given, T1 already given, Hg1 we can determine from the saturated water table based on the T1 temperature. Okay, so now we want to determine the omega 1 value because we want to determine the value of H1. So omega 1 equal to 0.622 PV1 divided by P1 minus PV1. So in this equation, PV1 we need to determine. P1 we already know the value is equal to the P total value, which is equal to 100 kilopascal. So now we need to determine the value of PV1. So PV1 we can determine from this equation, where PV1 equal to psi 1 relative humidity for state number 1 multiplied by PG1. Okay, where PG1 we can determine from the what we call saturated water table, where PG1 actually is equal to P saturated at T1 at 10 degrees Celsius. So from the table we can obtain PG1, where PG1 equal to P saturated at 10 degrees Celsius equal to 1.2278 kilopascal. Substitute the value of PG1 into the PV1 equation, so we will get PV1 equal to 0.368 kilopascal. Okay, then we already obtained the value of PV1 and also P1. Substitute the value of P1 and also PV1 into the equation of omega 1, and then we can calculate the value of omega 1, where omega 1 equal to 0.0023 kg H2O divided by kilogram dry air. Okay, next we need to determine the value of Hg1, where Hg1 equal to Hg at 10 degrees Celsius, Hg at 10 degrees Celsius, where we can determine by using the saturated water table. So based on temperature 10 degrees Celsius, by using the saturated water table, the value of Hg at 10 degrees Celsius equal to 2519.2 kJ per kg. So we already got all the information to determine the value of H1. So substitute into the equation of H1. So H1 equal to 15.8 kJ per kg dry air. Okay, settle for enthalpy for step number 1. So now we want to determine the value of H2 for step number 2, where Hg2 equal to Hg at 22 degrees Celsius. So we can refer to the saturated water table based on temperature at 22 degrees Celsius, where Hg at 22 degrees Celsius equal to 2541.0 kJ per kg. Okay, so substitute into the equation of enthalpy, where the enthalpy for state number 2, H2 equal to CpT2 plus omega 2 Hg2. So Cp2 already given, T2 already given, where T2 equal to 22 degrees Celsius, and omega 2 we obtain from omega 1, because during the heating section or heating process, omega 2 equal to omega 1. Hg2 will determine, and we just substitute all the information that we obtain into the equation for enthalpy H2. So we'll get H2 equal to 28.0 kJ per kg dry air. Okay, so now we need to determine the last parameter for Q in dot, where we need to determine the value of MA dot. So now we know that the partial pressure for the dry air PA1 equal to P total P1 minus PV1, the partial pressure of water vapor at state number 1. Okay, substitute the value that we have. So partial pressure of dry air at state number 1 equal to 99.63 kilopascal. Use the ideal gas of air equation, where we have PVRT, the formula for the ideal gas equation, where PA1 V1 equal to RA T1. So if you rearrange the equation, so the equation will be V1 equal to RA T1 divided by PA1 will be equal to 0.815 meter cubic per kg dry air. Okay, so from the value of V1 also V1 dot volume flow rate that given in the question, so we can determine MA dot, where MA dot equal to V1 dot divided by V specific volume V1 equal to 55.2 kg per minute. So we already got all the data for Q in dot, so substitute into the Q in equation. So Q in equal to MA dot multiplied by H2 minus H1 will be equal to 673 kilojoule per minute. Okay, so that the value of the rate of heat supply in the heating section. Okay, for question B, we need to determine the mass flow rate of the steam. The steam that produced by the humidifier in the humidifying section. Okay, so we have this diagram and we have the data given for the problem. So in the humidifying section, in terms of equation, so we have we need to use, in order to determine the mass flow rate of the steam, we need to use the water mass balance equation. MA2 dot multiplied by omega 2 plus MW dot equal to M3 dot multiplied by omega 3. So the mass flow rate of the steam refer to the value of MW dot. So rearrange the equation, so we will get the formula for MW dot, which is referred to the mass flow rate of the steam, where MW dot equal to MA dot multiplied by omega 3 minus omega 2. So now we already calculate the value of MA dot and also the value of omega 2. So now the remaining term that we need to determine is the value of omega 3. Okay, so for omega 3 we need to determine the value of Pg3, where Pg3 equal to P saturated at 25 degrees Celsius, where we can determine this what I call this value by using the saturated water table based on temperature. So at 25 degrees Celsius we can determine the P saturated value, where the value is equal to 3.1698 kilopascal. So by using the equation for the omega as shown in this slide, where omega 3 equal to 0.622 relative humidity at state number 3 multiplied by Pg3 divided by P3, where P3 actually equal to P2 equal to P1 equal to 100 kilopascal, minus psi 3 relative humidity at state number 3, and also multiplied by Pg3. So Pg3 will determine where the value is 3.1698 kilopascal, and the value of psi 3 relative humidity for state number 3 already given in the question, which is equal to 0.6. So substitute all the value, so you will get omega 3 equal to 0.01206 kilogram H2O divided by kilogram dry air. Okay, so now substitute all the value in terms of MA dot, omega 3 and also omega 2 into the equation for mass flow rate of the steam, MW dot. So we'll get MW dot equal to 0.539 kilogram per minute. So this is the answer for the mass flow rate of the steam. So if the question asks you to describe or to draw the process involved in the equation, so you can use what I call the simplified psychometric chart to describe the process. So you need to draw the what I call relative humidity line, specific humidity line, temperature line, and find out the intersection point for state number 1, state number 2, and also state number 3 as shown in this slide.